we have another theorem which states that a splitting field implies that the field is also finite and it is also an algebraic extension. That means if we have some splitting field of the polynomial f of x, then that splitting field, which is represented by this k, is both finite extension as well as it is an algebraic extension of f. So let us prove it. We have given f and its splitting field as k for this polynomial f of x in capital F of x. So this is given to us, right? For that we assume k as the splitting field of polynomial f of x. If alpha 1, alpha 2 up to alpha n, they are the roots of that polynomial. So by definition of splitting field, we can write k to be the lower field where all the roots alpha 1, alpha 2 up to alpha n of that particular polynomial have been adjoined to this. So this is the thing. Next, according to this thing, we say k is finitely generated extension where all these elements alpha 1, alpha 2 up to alpha n, they are finite in number. So k acts as a finitely generated extension which is generated over f by all the roots of f of x. So we can now construct another polynomial ki, where we say, so k was the polynomial where all the roots alpha 1, alpha 2 up to alpha n were adjoined. So in between I can say I have some field ki where only the first I elements are adjoined. So that means this would be smaller than ki plus 1, which would further be smaller than ki plus 2, and so on. This would be the last kn, which is equal to k, right? So we have constructed it like this. And what would be k naught? K naught would simply be equal to f only. And what would be k1? K1 would be f where only alpha 1 has been adjoined, and so on. So this is the construction. So we say ki is of this form and alpha I is an algebraic element over ki minus 1 where k naught is f according to this construction. Then we say f is contained in ki and ki is contained in k. Moreover, I can write this ki or k1 to be this k naught into alpha I. So ki would be ki minus 1 into alpha. So what would be the degree of this whole extension field over the lowest field, that is f? So the degree of this ki over ki minus 1 is ni, which is the degree of minimal polynomial satisfied by alpha I in ki minus 1. If its degree is ni in general, so what would be the degree of all the fields? So we are interested to calculate what is the degree of this upper field k defined over this lower field f. So we will use the result where the degrees are broken down into the product of the lower degree, the degree of this over this, the degree of this over this, this over this, this over this, this over this, and so on, this over this, this over this, right? So the degree of k over kn minus 1, what is k? K is basically kn. So kn over kn minus 1, kn minus 1 over kn minus 2, so on. K1 over f is k naught, right? And we have written down this to be equal to ni. So this would be nn, this would be n minus 1, to this would be n1. So which is the product of finite numbers. So this product would also be finite. If this is a finite, that means the degree of this polynomial is finite. We can say k is a finite extension over f. And we also have the result which says that every finite extension, that is an algebraic extension. So we say k is also an algebraic extension over f. So this is the proof for this theorem, which says that if you have some splitting field, then that is also a finite extension. Moreover, it is also a algebraic extension.